So today we're going to demonstrate how to prepare an agarose gel, how to load an agarose gel, and run an agarose gel. Basically 3 steps. So the first step is one of the most difficult, and that's preparing the gel. Okay, preparation of a gel, pouring of a gel. This gel is already poured. You can notice the tape. Here's the comb that allows us to create the wells for the gel. Is one of the trickiest parts of preparing the gel. In that, you have to tape the ends. In some ways, this is the most hazardous part of the preparation, because if this tape isn't a tight seal, the gel will leak when you pour it. So you have to run your finger along, make sure it's tightly sealed. Okay. So now we're ready to pour the agarose into this gel. This one I've already done. So this is the one we will use when we load the gel. So let me go and get the agarose and I'll show you how we pour this. Alright, this agarose is purified agar. About 4 to 5 millimeters. This has to be put back in the water bath. So far looks good. No leaks. Alright. Let's put this back in the water bath and then we'll load this gel. Alright, let's remove this tape. Not always easy. See the thickness of the gel? Thickness is about 4 or 5 millimeters. All right, now we're ready to add buffer. You may notice that the red dot and the red band match up. The black represents the cathode, or I'm sorry, the anode. The red represents the cathode. Let's pour the rest of the buffer. There's a little subtlety with respect to pouring. Let's just cover the surface. It is always best to have a little buffer before you remove the comb. The comb pulls out a lot better if you have some buffer. Now, if you look on this gel, there are little dimples, and we want to remove all the little dimples. Add just enough buffer to just remove the dimples. Okay. So we're going to load 4 lanes. Lane 1 will contain a 1 kilobase ladder of DNA. Lane 3 will contain DNA, lambda DNA, that has been digested with a restriction enzyme. We're not sure which one it is. Lane 5 is lambda DNA that's been digested with Hindi 3. And lastly, lane 7 will be lambda DNA undigested. So we're going to load 4 lanes. 10 microliters of the solution into 4 lanes. Okay, let's load this first lane. Notice the blue color. These samples have loading dye, which is a mixture of 2 dyes plus some sucrose to create heaviness to the solution itself. It's important that you not puncture the gel. And you may remember we had a video that talked about that, but you hold the tip directly over the well. So let's load the rest of the samples. Okay, let's hook up the power supply. This is nice because it's color-coded. All right, let's set the voltage. We're going to set it at 100 volts. We're going to give it a real, whoops. The voltage set. Click on Run, and we're good to go. Now, the higher the voltage, it's essentially the more force. So, we're running at 100 volts. That's really pushing the DNA through the gel. The higher the voltage, the more force you have, the more rapidly the DNA moves. And so, if you run at a lower voltage, you'll be able to more carefully resolve the bands of DNA. Most of the time, we're not concerned about resolution. We're just happy to get the bands. So traditionally, we run at 100 volts. But as I say, if you want a more refined gel, you would run at a lower voltage. But you also have to run it longer. So the higher the voltage, the faster. And we are going to do that today and see how our gel works out. So let's look at the gel, because there are some features of the gel or some features of this run that tell us the gel is working. So you may remember from chemistry, what was the old rule? Cations to the cathode. Cations to the cathode. What cations are we talking about? Well, electrolysis is splitting water, and the cations we're dealing with are protons. And what happens when you move protons to an anode? You get hydrogen gas. So we're hopefully going to be able to see these hydrogen gas bubbles. It's just like when you did that experiment when you were a kid, the electrolysis of water, hydrogen and oxygen. So at the anode, we're going to have oxygen. At the cathode, we're going to have hydrogen, and hopefully we'll be able to view that. Also, we'll be able to see movement of the dye, which will be the leading edge of the gel. So hopefully we'll be able to view that pretty soon. All right, as we look at this gel, we can see the oxygen and hydrogen bubbles forming at the respective anode and cathode. And then as I look down on the gel, I can see that my dye is moving, so I know the gel is working. Everything is working fine. We'll let this run half an hour, 45 minutes, and then we'll view it with the gel viewer. Some last thoughts. Remind you, DNA is negatively charged, so it's going to be moving to the positively charged electrode, namely the anode. So DNA moves towards the positive charge. DNA is negatively charged. Keep that in your mind. Okay, thanks. All right, let's look at the results from our agarose gel from a diagrammatic point of view. In lane 1, we had the 1 kilobase DNA ladder. So the bands that you see, although they're smeared, and that happens sometimes when you run it at 100 volts, the lanes, or the bands I should say, are not well resolved, but that's okay. Lane 1, 1 kb ladder. So this furthest gel, the smaller the molecular weight, the more rapidly it moves. And then on 3 and 5, we have basically a lambda DNA Hindi 3 digest. Theoretically, there are 8 bands, but since these bands are not resolved, we only see 4 or 5 bands. So 3 and 5 are basically identical. If you look at the diagram, you'll see that that's the case. So these represent restriction digest of essentially a DNA fingerprint, if you would, of the lambda DNA. In lane 7, high molecular weight, uncut lambda DNA. Okay, so it moves the slowest of anything that we have, roughly 43,000 base pairs. I might also point out that there is a bright band at the source of lane 7, and you might think about that. It virtually didn't move at all, and that is probably residual chromosomal DNA that was part of the original preparation that was used to make the lambda DNA. So it's so big that it virtually remains right by the well. So lambda DNA, Indy 3 digest of lambda DNA. The bands are a little smeary, but our gel worked pretty well. So, all right.